Now, you can use some normal distribution tables that are in the back of the book to find the probability that a value lies between certain boundaries that I'm going to give you, but we're not going to use those tables in the back of the book for anything. So if you're working on homework and you get to an example and you click view example, and that um, hint from MyLabs Plus tells you to look at a table in the back of the book, that's not how we're doing any of these problems. I'm going to show you how to find this area on the calculator. I'm going to give you a standard normal distribution. I'm going to tell you, because it is a standard normal distribution, the mean is 0 and the standard deviation is 1. And then I'm going to give you some lower boundary and upper boundary and ask you to find the probability or the area of any randomly selected value lying between that lower and upper value. On the calculator, that is under your VARS menu, right above the VARS button on your calculator. It says distribution, DISTR, and to access the function that we need, I'm going to press second and VARS. And then choose normal CDF number 2, and I'm going to give the calculator the left boundary and the right boundary that I was given. Now, the reason that I'm using normal CD or normal CDF instead of normal PDF is, remember, the C stands for cumulative. It's adding up all the probabilities between the left boundary and the right boundary that I'm given. So I'm going to use normal CDF, and then I'm going to type in the left score that I'm given and then the right score that I'm given. All right, an example of a standard normal distribution could be thermometers that are using the Celsius scale. 0 on the Celsius scale corresponds to the freezing point of water. So if we were manufacturing thermometers, we would want the mean reading of those thermometers when in an ice bath, we would want the mean reading of those thermometers to be 0. That's what they're supposed to read at the freezing point of water. So let's assume that we have a lot of thermometers manufactured by the Precision Scientific Instrument Company, and the mean reading of the thermometers is 0, and the standard deviation of the readings is 1. Also assume that the readings are normally distributed. If we randomly select a thermometer, we want the probability that it reads between -2 degrees and +1.5 degrees. Well, it's supposed to read 0 degrees, but anything man-made is going to be a little bit off. And so we want the probability that a randomly selected thermometer has a reading between -2 degrees and +1.5 degrees. We're looking for this area within the normal distribution. Since we're looking for an area, we're going to use the distribution button, which is right over our VARS button, and second VARS, choose number 2, normal CDF, and then simply enter that left boundary and right boundary that I was given. I want the probability that the reading is between -2 and 1.5. My comma is right over the number 7. I need to use -2, comma 1.5, and then enter. The probability that an individual thermometer will have a reading between -2 and 1.5 is about 0.910. That means that if I pulled very many thermometers from the ice bath and recorded their readings, 91% of them, just the 0.910 changed to a percent, 91% of them would have readings between -2 and 1.5. What about finding the probability that an individual thermometer would have a reading less than 1.27? Well, again, the mean reading on all the thermometers at the freezing point of water is 0. I want the probability that a particular thermometer has a reading less than 1.27. To which side of 1.27 would the mean be? 1.27 is a little more than the mean, a little less than 1.5 standard deviations, a little more than just one standard deviation from the mean. And we want the probability that a thermometer has a reading that's less than that. Well, less than 1.27 is to the left of 1.27. So that's the direction I've shaded. The only thing is, when I'm using normal CDF, I have to enter a left cutoff score and a right cutoff score. I don't have a left cutoff score here. I'm shading forever to the left. Less than 1.27 would be all the way out off the graph to negative infinity, and I can't use negative infinity as a cutoff score. When that happens, we're just going to use such a small z-score that there really isn't going to be any area to the left anyway. For that very small z-score, when we shade forever to the left, we're just going to use negative 9,999 as our left cutoff. If we were looking for the probability that a thermometer would have a reading more than 1.27, we would enter positive 0.9999 as our right cutoff. But here I want to enter normal CDF. I'm shading from negative 9,999 up to positive 1.27. So this is exactly what I'm entering on the calculator. Second VAERS, number 2 for normal CDF, left score negative 9,999, comma, right score 1.27. That probability rounded to 3 decimal places is 0.898. That means that a probability of a randomly selected thermometer will have a reading less than 1.27. The probability is 0.898, or if I change that to a percentage, 89.8% of the thermometers will have a reading below 1.27. If the thermometers are supposed to read 0 degrees at the freezing point of water, then about 90% of them at least are going to read below 1.27 degrees. If one thermometer is randomly selected, find the probability that it reads above negative 1.23 degrees. Well, think about where that would be in relation to the mean. The mean is 0, and a reading of negative 1.23 would be somewhere below the mean. I want the probability that a thermometer reads above that, so I'm going to shade to the right of that. And when I enter this information in normal CDF, I always have to enter the left score and then the right score. It always has to be in that order. So on the previous example, my left score was negative 9999 and my right score was 1.27. The numbers have to be in that order. And on this example, my left score is the negative 1.23, and I'm shading forever to the right. When I'm shading forever to the right, I'm going to use positive 9,999 as that right cutoff. So I enter normal CDF, second Bayes, number 2. I want the probability from negative 1.23, comma, to positive 9999, and I get that probability to be 0.891 when I round it to 3 decimal places. That means the probability of randomly selecting a thermometer with a reading above negative 1.23 is 0.891, or about 89.1% of thermometers will have a reading above negative 1.23. So in the previous 3 examples, I was either given a left and a right score, or I was given a right score and shaded forever to the left, or I was given a left score and shaded forever to the right. But in all 3 cases, I was looking for a probability, or a probability is the same as the area under the curve from my left score to the right score.